Hey everyone, and welcome to Stochastic All the Things, ray tracing and hybrid real-time rendering. My name is Tom, and I work in Stockholm in SEED. SEED is a technical and creative research division of Electronic Arts. We are a cross-disciplinary team with a mission to explore the future of interactive entertainment. One of our recent projects is an experiment in hybrid real-time rendering, deep learning, and procedural level generation. You might have seen this video, but I'm going to play it anyway. Sorry for the choppy frame rate. My laptop is really convinced it's going to run out of power at some point, but you can check out the video on YouTube, and I promise it'll be smoother than that. Pikapika is a mini game that we built for AI agents rather than humans. And through the use of reinforcement learning, the agents learn to navigate and interact with a virtual environment. They run around fixing those cute machines so the conveyor belts can keep running. If you're interested in the artificial intelligence part, do check out our paper in archive. It details how we train the agents, what they see, and how they communicate with the game logic. We built the minigame from the ground up in our Halcyon R&D engine. It is a flexible experimentation framework that's still young, yet capable of rendering shiny pixels. And thanks to a collaboration with NVIDIA and Microsoft, we had the opportunity to work with an early version of DirectX Raytracing and explore some of the possibility space of this technology. We had kind of guessed what other developers might create with it, and we deliberately set out to create something a bit different. We wanted cute visuals that would be clean and stylized, yet grounded in physically based rendering. We aimed for something that would show the strengths of ray tracing, while also playing nice with our tiny art department. So we only had 2 artists at the start of the project, and 1 joined a bit later. In order to create interesting variety, we used a procedural level generation algorithm with a compositional balance algorithm that drove layout and asset placement. And then to retain sanity, we forewent baking, proxy building, level of detail, and generally any kind of content hacks. But before we dive into the shiny pixels, let's have a bit of a breather and look at the map. While this talk is about all things stochastic, it is definitely mostly about ray tracing. I'll discuss how the latter can be used to render previously difficult phenomena such as reflections, refractions, translucency, indirect lighting, and shadows. But why would we even use ray tracing, right? Well, if you're a graphics nerd, the question doesn't even need asking. Well, we want to use it because it's cool. It's been the holy grail of computer graphics for the past few decades. And we might finally have the chance of killing that phrase, ray tracing is the future and ever will be. But let's put things into perspective. Ray tracing isn't the very thing to be excited about. It's just shooting rays, right? But it's what we can do with it. So for example, one can write a path tracer in just a few hundred lines of code, and it will start producing photorealistic images like the one here. Unfortunately, path tracing is not very fast. This image took around 15 seconds to generate on the top end of the GPU. And there's still some tricky noise left in it, which might take hours to converge because of difficult light paths such as caustics. And then a 1 sample per pixel image looks considerably noisy, and even this is kind of expensive to render. But the good news is that we can render this image at real-time frequencies on today's hardware using hybrid rendering. It is not quite the same as the path trace version. It is missing castings and some small-scale interreflections, but I would say it's pretty close. So let's compare it to a version without ray tracing. Yeah, it's not very pretty, and this is not a hello world kind of render. It already includes a number of non-trivial algorithms such as screen space reflections, state-of-the-art screen space ambient occlusion, physically based rendering, temporal anti-aliasing, cascaded shadow maps, and so on. Even though some people suggested that it might not be a fair comparison, because if this was a game, then you would apply some classic game industry solutions, and for example, fix the light leaks and reflections with local refraction probes, then the floor is mostly flat, so maybe you could apply planar reflections to it, and then lighting can be baked as well for the GI and so on. On the other hand, this rendering pipeline is and why ray tracing is so awesome. This rendering pipeline is just a toggle. So you enable it and you get good results by default. And it doesn't require any artist hacks and artist time. So what is this magic pipeline? Well, glad you asked. It's a hybrid of classic rendering techniques with some ray tracing sprinkled on top of it. We have a pretty standard deferred shading pipeline with compute-based lighting, a pretty standard post-processing stack, and then we have a few pluggable components. We can render shadows via ray tracing or via cascaded shadow maps. Reflections can be ray trace or it can be ray march in the screen space. And then same story goes for ambient occlusion, also ray tracing or ray marching. Only our global illumination and translucency and transparency actually require ray tracing. And this rendering pipeline is built on top of a rather flexible material system. It mostly came to mind because of my dislike of the metalness trick, where you have a lerp factor between how dielectric and metal something is. But despite this silly motivation, it allowed us to rapidly experiment with the looks for our demo and easily match the output of ray tracing-based renderers. It doesn't explode during this experimentation either, because we enforce energy conservation, and we blend between layers using Fresnel equations, so it is all physically plausible. And then this material system works with all our render modes, be that the pure raster, the hybrid, or the ray tracing. And this is where DXR shines. You can reuse code across all those effects and shader stages. And this means, for example, that if you validate your path tracer against a good known renderer, such as Mitsuba, you can then validate your other techniques against this reference and make sure all of your rendering is consistent. So as soon as we actually had a good working path tracer, we started the journey into hybrid rendering. And the first domain we explored was reflections. We shoot rays from the G buffer using the position and normal and other information. We shoot them at half resolution, which means that for every 4 pixels, there is a single reflection ray. Then usually when you have a hit point, that point needs shadowing as well, meaning that we trace another ray, bringing it up to a total of 1/2 ray per pixel. And it may not seem like much, but we can actually get quite a lot from that if we apply reconstruction and filtering. So we run a multi-stage algorithm which denoises the reflections and brings them up to full resolution. And it works on arbitrary surfaces with spatially varying normals, roughness, and different material types. The reflection system comes with its own pipeline. We start by generating arrays via importance sampling. And this gives us rays that follow the properties of our materials. Then scene intersection can be done via either screen space reflection or ray marching, or ray tracing. And in the case of the former, SSR can report failure, for example, when a ray tries to go behind an object. And then that can be picked up by an environment map gap fill solution. And what's interesting is those intersectors can be chained after one another. So when SSR reports failure, then ray tracing can actually pick up where SSR last left off and continue the ray. Now, once intersections have been found, we proceed to reconstruct the reflected image. Our spatial kernel reuses ray hit information across pixels, upsampling the image to full resolution. It also calculates useful information for a temporal accumulation pass. And finally, we run a last chance noise cleanup algorithm in the form of a pretty simple cross-bilateral. And then the SSR bits are not very interesting for this presentation. They have been talked about for years. So we're only focused on ray tracing. So the first pass, the reflection sampling, is a pretty simple one. Given an I direction, we need to generate a reflected ray matching the BRDF. Sampling from the complete BRDF function is rather involved, so we only import and sample from the normal distribution. So we picked a microfacet normal, reflect the I vector off of it, and we get a ray direction. But since we only have a quarter array per pixel, we must ensure that we get a high-quality distribution of those reflection vectors. And the very minimum we can do is use a low-discrepancy quasi-random sequence, and halton is usually a safe bet. We then couple it with per-pixel jitter of those generated samples, known as Cranley pattern zone rotations. And then from every point in this 2D primary sample space, we generate a reflected direction. Because we're sampling from the normal distribution alone and not the full BRDF, we actually may end up with vectors which are implausible and go below the horizon. There are fancy ways of dealing with this problem, such as sampling from the visible microfacets that Eric Heiss detailed, but we didn't have quite enough time to investigate it for our demo, so we simply detect this case and just re-roll the ray. The reflection pass works with our layer materials and still generates just one direction for the whole stack. The simplest way to accomplish this would be to choose one layer in the stack by random, for example, with uniform weights, and then sample from that specific layer. This works, but can be quite wasteful. For example, a smooth dielectric clear coat layer will be almost imperceptible heads-on, but when you look at grazing angles, because of Fresnel, it dominates the full reflection, which means that if we uniformly distribute the layers between stacks, we will be wasting rays in some cases. So to improve on this scheme, we draw the layer itself from a probability mass function based on the layer's approximate visibility. It is also important to keep in mind that multiple layers could potentially generate the same direction. It is pretty significant because we later use those rays and their probabilities in the spatial reconstruction pass. And then to make this pass oblivious of which layer the ray came from, we have to add up the probabilities so that the ray looks like it came from the whole stack and not from the individual layer. And since we reuse rays across a number of different techniques, such as the SSR, the gap fill, and ray tracing, our ray generation pass is separate from the DXR raygen stage, which makes the raygen a trivial shader. It just reads the previously generated ray direction, calls trace ray on it, and that's basically the same as a path tracing function, and then outputs the results into RGBA16F textures. And besides color, we output some useful information for the reconstruction, such as the ray direction, the inverse probability of having sampled the ray, and the hit point, the hit direction, sorry, hit time. And after all this work, we get something like this. It more or less resembles the reflection component of the path traced image from a few slides back, except this one is half resolution and doesn't do the recursive bouncing. So you may be asking yourself, like, why go through all this trouble just to generate a noisy image? And why don't we just start with mirror-like reflections and blur them as a post-process? And it is a valid question, and I think the right answer is somewhere in the middle. So stochastic sampling is prone to cache thrashing. Cache thrashing produces all sorts of noise. On the other hand, a post-processing filter may introduce light bleeding because the whole gather area will potentially bleed across walls. And then it can still produce noisy outputs if you have high-frequency information in the scene, such as high-frequency normal maps. Besides that, the non-stochastic approaches can suffer a bit more from structured aliasing, like fences and staircases and so on. And that kind of aliasing is usually more difficult to filter out than plain noise. So in practice, those non-stochastic approaches could well produce more objectionable artifacts than stochastic ones. That being said, those noisy or stochastic approaches have a tendency to amplify variance present in the scene. So for example, a horror case is tiny emissive lights, because the chance of hitting them is very low, but when you do hit them, suddenly the intensity is super high. So perhaps there's a solution somewhere in the middle where you can kind of change how stochastic the approach is by just lerping between stochastic and non-stochastic, or maybe you can use pre-filtering. And some research is still required in this area. But our reflection pipeline is already a step in that direction, more or less, combining stochastic sampling with spatial reconstruction. And in practice, we actually bias our primary sample space to make the rays travel more towards the perfect mirror direction. And then we cancel some of this bias in the spatial reconstruction. So once again, this is the raw ray trace output. And this is what the spatial filter does with it. The output is still noisy, but it's now full resolution, and it gives us a variance reduction similar to actually having shot around 16 rays per pixel. And the idea behind it is very similar to the stochastic screen space reflections, which I presented 3 years ago at SIGGRAPH. So I will not go into too many details, but as a quick recap, every full resolution pixel uses a set of those ray hits that were intersected by the pipeline, and it reconstructs the reflection. And it's basically a fancy weighted sum, where the local pixels BRDF is used to scale the intensity, and the ray's own PDF is used to reduce it. And recently, Eric Heitz, Stephen Hill, Morgan McGuire, and Ari Silvenoinen pointed out that it is something called a ratio estimator, so apparently the math is pretty sound. A few shortcuts here and there mean that it cannot be unbiased or even consistent, but it works pretty well in practice. And in practice, the code is super simple as well. As mentioned, it's just a fancy weighted sum. What is a bit more interesting is the set of rays that each pixel uses in the reconstruction. So suppose we took the same set of rays across all the pixels, and because our hit buffers are half resolution, we will be using the same data for every pixel in a 2x2 tile, and thus we get half resolution results. We can fix that pretty easily by using disjoint ray sets between those 4 pixels in a 2x2 block. So we need 4 sample sets, which are 4 pixels we use in the quad. And those samples should be well distributed between each other, and ideally should be as disjoint as possible. So I don't know about you, but this screams blue noise to me. And here is this one weird trick. So we start with uniform blue noise, and we threshold it into 4 classes, like this. And then the class determines which pixel the sample position goes to. So we just pick a center somewhere in the middle of this blue noise and treat the coordinates of the respective pixels as offset to sample into the ray buffers, and this is our distribution. We can even sort the positions by distance to the center and use those in adaptive kernels where you vary the number of rays your samples use to get more filtering, but potentially more bleeding as well. So this is more or less the idea behind the spatial reconstruction filter, which is then followed by temporal accumulation to further clean up the image. And finally, by a much simpler bilateral filter that removes some of the remaining noise. It is a very blunt instrument, which overblurs the image, but we needed it to handle some of the rougher reflections. So compared to screen space reflections, ray tracing is trickier because we can't cheat and use a blurred version of the frame buffer to get a pre-filtered radiance value. So because there's much more noise, our filters need to be much more aggressive as well. But we can still tell this filter to cool it unless the image is actually noisy, or locally noisy. So we estimate variance in the image in the spatial reconstruction pass and use it to drive or steer the bilateral kernel. So the variance then controls how many samples and how wide the kernel becomes, preventing overblurring. Finally, we throw all of this at temporal anti-aliasing and get a pretty clear image at the end. So it is important that this all comes from a quarter array per pixel per frame, and it works with dynamic objects and camera movement as well. And movement is particularly difficult for temporal techniques, as they need to perform reprojection to correlate images between frames. And this isn't always trivial. We actually have 2 very different methods of reprojecting reflections. So we can use the motion vector of the reflector, which we have basically for free because a whole lot other techniques use it, such as motion blur and TAA. And that one is the line below. And then we can use, then reflections have their own parallax. They kind of move independently of the surface which reflects them. We can track that by calculating the average distance to the hit points and reprojecting the average hit between the two frames. And this is the line on the top. As you can see, they're quite different. So we have two very different strategies, but who says we have to restrict ourselves to just one? But if you consider a few cases, none of those techniques clearly dominates as well. So per pixel motion vector works pretty well for rough and curved surfaces, for example, the robot's head, but it fails a lot with shiny surfaces. So check it out on the left. So the robots are pretty cool, but the ground is horrible. And then hit point reprojection works pretty well for the floor, but fails spectacularly on the robot's head. Yeah, as I mentioned, who says we have to use just one method? Why not both? Why not reproject using both of those techniques and then blend between them depending on how well they fit to the new frame? We can build pretty simple statistics from the newly generated frame and use them to score the two reprojection methods. For example, if we calculate the mean color and standard deviation for every new pixel, we can define a distance metric and use it to weigh the reprojected values. So check out the result and pay attention to the floor and the little robots. So this is certainly not there yet, but it works better than using one of those schemes alone. And this is just some arbitrary math just kind of tapped out on the keyboards. But what is left is mostly just this occlusion. And as Brian Carr's, Hugh Mullen, and Tim Lutz pointed out in the temporal anti-aliasing saga, we can use basically the same local pixel statistics to build a bounding box of plausible values on the new frame and use them to either reject or clamp the values reprojected to force them to fit to the new distribution. We can still use the dual source reprojection, but we now weigh and accumulate the clamp contributions. Now, this clamping is not a free lunch, and it biases the result and can cause some flickering, but it definitely cleans up the ghosting pretty nicely. Now, thanks to ray tracing, we can scatter lighting not just in empty spaces, but inside volumes as well. And this enables realistic refractions and translucency. In our Halcyon framework, we have implemented those as separate yet closely related effects. For refractions, we support multiple interface transitions, rough surfaces, and light absorption as it travels in the medium. The technique is order independent and meshes seamlessly with other rendering phenomena. Our translucency is a simple yet effective method inspired by Colomber-Brisebois' work in Frostbite a few years ago. The most important difference is that we skip pre-computation and dynamically scatter light inside the medium. Both translucency and rough refractions require multiple samples in order to converge to a noise-free result. Those are also difficult to filter because of the possibility of multiple layers overlapping. Currently, the best, most successful denoisers assume just one layer of surfaces, which makes the screen space filtering intractable. Perhaps some solutions exist around deep frame buffers, per pixel linked lists, and full 3D denoising, but we didn't have quite the time to investigate those for our demo. So we cut corners and use texture space integration. And while this goes against our goal of not requiring parameterizations, translucency and refractions were used quite sparsely, and we could afford to unwrap a few objects. And static space allocation in textures provides a stable integration domain, which we can time slice over a budget of, say, 1 million rays per frame. And here's a breakdown of how we compute translucency. We first dynamically render textures with normal and position information for all the users of translucency. We generate a ray from every such valid position and use the surface normal for direction. We then flip the ray and push it inside the object. From that location, we generate translucency rays, which will travel inside the medium. We calculate lighting at that location, and we gather all the samples from it. Finally, we update the values stored in the texture. And this is an extremely crude approximation, and any volumetric people in the crowd are probably cringing, as this should require things like phase functions and multiple scattering, but even this crude hack produces pretty good-looking results for us. And we let the results converge over multiple frames via temporal accumulation. Spatial filtering can be used as well, but we didn't hit enough noise to actually warrant make it worthwhile. And since lighting conditions can change with objects moving, a temporal filter needs to be able to adapt to them. Depending on your use case, a simple exponential moving average may do the trick. We use a slightly fancier adaptive temporal filter based on exponential averaging. It varies its hysteresis, or the blending rate, to quickly reconverge to dynamic change in conditions. And I'm going to cover it a bit later in the section of global illumination. A similar approach as for translucency is used for refractions, such as glass. The major difference is that we warp the rays against the view's origin. For clear glass, the refraction can be based on good old Snell's law, but for rough glass, a scattering function must be used, which generates rays refracted of microfacets to widen the cone of refraction for rougher interfaces. We trace a ray in a scene, sample lighting, and finish by modulating the results by the medium's absorption according to Beer's law. And chromatic aberration can also be used. And neatly, DXR provides us information about which side of the phase we're hitting. So we can track the current index of refraction, knowing whether we're inside the medium or outside, and correctly handle the transitions with total internal reflection. The interaction of refractive surfaces with light is definitely not completely solved, though. For shadow rays, we assume that objects are fully opaque, and this causes some energy loss. And to handle shadows for this innocent-looking pen, we would actually need caustics, because the shadow rays actually bend. And that is for another time, because caustics are some of the most difficult problems to handle in rendering. So we've now covered indirect, specular, and transmission. So let's talk about the rest of light transport now. I mean, indirect lighting applied in a diffuse manner to scene surfaces. GI makes scene elements fit with each other and makes the life of artists easier, as it reduces the need to manually place fill lines and tweak surface colors. We set out to create a solution that was dynamic without the need for any pre-computation or even UVs. It had to support dynamic and static scenes, and we wanted it to converge to a high-quality result, or refine to high-quality results, at least in static regions. To motivate the importance of proper GI, have a look at one of our early test renders without it, and now compared to one with indirect diffuse lighting. I think the difference is striking, and motivated us to actually go from a prototype to the final implementation. It was obvious from the start, though, that we didn't have the GPU budget to fully solve GI every frame. Some sort of spatial or temporal accumulation would be needed. With a path tracing integrator and all our other rendering already there, we could only afford around a quarter million rays per frame to generate GI. The most important decision to make was to whether accumulate in screen space or in world space. There have been a few techniques that successfully perform spatio-temporal integration in screen space by using fancy filters. And they kind of work, and the nice side effect of those is that if you move the camera close to a corner, you actually get increasing resolution. You move further away, and you still retain the same distribution of samples across the scene. But those techniques typically showcase only static environments, and we were really afraid that ghosting will be ruining our day with our moving agents. So we actually went with world space storage for our GI accumulation in a form of dynamically distributed circles. So each of those will be represented with a position, a normal, a radius, and some additional information. Having them persistent meant that we could reliably accumulate over time and never worry about disocclusions. A free-form cloud of circles also means that no parameterization of the scene is necessary. And then by giving them smooth fall-off during rendering, we also obtain smooth results. The circles can also be skinned in order to support animated objects, so they remember which object they respond on, and they move with it every frame. And this does pose a challenge for temporal accumulation, but it is not as severe as ghosting from screen space techniques. To apply surfels to the screen, we render them in a similar way to light sources. We use smooth step for distance attenuation with the Mahalanobis metric to squish them in the normal direction. We also have angular falloff, but each surfel's payload itself is just irradiance without any directionality. And similarly to deferred lights, we have a culling system. In order to be able to query the GI solution anywhere, we use a world space data structure. For simplicity, it is a grid in which every cell stores a list of intersecting surfels. Each pixel or point in space can then query the structure and find all the relevant surfels. The GI has limited resolution and lacks high-frequency detail, so we augment it with screen space-based ambient occlusion implemented after Grand Truth AO from Jorge and colleagues. And we use the colored multi-bounce variant of it, as it helps to keep the warmth in our Tor-like scenes. As I mentioned, surfels are spawned on the fly and require no precomputation. Here's a clip of the process in action at around 1% speed. As you can see, the distribution is quite even and resembles the Poisson disk distribution. You get no clumping of the surfels in some areas, and it's pretty pleasing to the eye to look at it. The placement algorithm uses gbuffer information, and it is an iterative hole filler. We start by calculating the coverage of each pixel by the current surfel set. We are interested in pixels with low coverage, since we would like to spawn new surfels in those locations. So in order to find best candidates, we need to find the worst coverage across the screen. We do it by dividing the screen in tiles, and then for each tile we find the lowest coverage using some thread group atomics and wave operations. Now, having found the point, the pixel, we can spawn a new surfel at this location using gbuffer, normal, and depth to reconstruct the world space data. And now, it is important to spawn the surfels probabilistically. So suppose you have a camera which goes very close to a wall, and then it's an area which doesn't have surfels yet, and suddenly all the pixels are shouting that they need new surfels, and then all tiles will also want to spawn in the same locations. But because we're very close to one location, you end up with tons of surfels in the same space. So the probabilistic spawning works by changing the probability of spawning based on the projected area of the pixel. Which means that we draw a number every frame in every tile and then decide whether to actually use the pixel or not, whether to reject it. And we continue this process all the time, basically every frame. And whenever there's poor coverage, we just spawn a new surfel in it. Now that we know everything about spawning surfels and applying to the screen, let's talk about how their irradiance is calculated. That part is actually super simple. We start by building a basic unidirectional path tracer with explicit light connections. We allocate more paths to the newly spawned surfels, so we don't initially look at noise. But we then decrease the number of paths to roughly 1 per surfel per frame. Full recursive path tracing, however, is a bit expensive, and for our use case, it is also unnecessary. We can exploit temporal coherence by reusing previous outputs and amortizing the extra bounces over time. So in practice, we limit the path length to just one edge, meaning that we shoot a ray and then immediately look up the previous frame's GI data. It makes the algorithm much closer to radiosity than path tracing, but the visual results are quite similar. And path tracing typically uses Monte Carlo integration to actually calculate values from this averaging. If expressed as a running mean estimator, it's an average of contributions with linearly decaying weights. Its convergence hinges on the integrand being immutable, though. And in our case, of the dynamic GI, the integrand changes all the time. So interactive path tracers and progressive light map bakers typically tackle this by resetting accumulation on change, so you get rid of the accumulated error. Their goals are different, though, and they try to converge to the correct solution and don't want any error. So in our case, our needs are a bit different, and we don't want the sharp cutoff. And since we cannot use proper Monte Carlo, we basically just outright give up on ever fully converging. Instead, we use a modified exponential means estimator, whose formulation is very similar to that of plain Monte Carlo. However, the difference is that the blending factor is in how the blending factor is defined. So in exponential averaging, the weight for a new sample is constant and typically set to a small value, so that the input variance will not be jarring in the output if you just scale it down by a tiny number. It is easy to notice, however, that if the input doesn't have high variance, then the output will not either, so we're kind of potentially wasting convergence speed. And we can potentially use a higher blending factor when we detect that variance is low. However, the specifics of our integrand change dynamically all the time, and we need to figure that out from the scene. So to figure it out, we use short-term statistics of mean and variance to inform the long-term blending factors. And they give us the idea of the plausible range of values that the samples should fall into when you generate new ones. They should fall within like 2 sigma, for example. And when they start to drift, we can increase the blending factor as well. And this is illustrated here with the adaptive integrator marked in red. The blue line is just a regular exponential blending, and it clearly has a hard time following what's going on. Meanwhile, the short-term statistics marked in gray inform our adaptive estimator of probable changes in the scene, making it adapt faster, yet converge with similar precision to the exponential averaging as well. And so while ray tracing helps with global illumination, it is certainly not a game changer for it. Where ray tracing does improve the state of the art dramatically is shadow rendering. Hard shadows become trivial. You just launch the ray, check if anything blocks it, and just write out the results. And soft shadows are pretty easy too. So you launch the rays in a cone, and you get variable penumbra, contact hardening. At least it's easy to get a noisy result, but we can still filter it pretty efficiently without shooting any new rays. We implemented a denoiser based on NVIDIA's spatiotemporal variance-guided filtering paper. And for those unfamiliar with the algorithm, it is basically temporal accumulation coupled with a multipass blur. And the blur's footprint is varied depending on the local variance. A spatiotemporal estimate of that variance runs before and during the blurring to control it. And an important aspect to note is that it is a general denoiser, which doesn't actually have any domain-specific knowledge of shadow casting. It still produces very realistic shadows. And let's zoom in on some of the details. We can see that we get sharp contact hardening and also get rid of the noise in the soft penumbra regions, and we don't overblur when it's not necessary. We only modified SVGF a bit in order to tailor it to our use case. And most importantly, we wanted it to be more reactive in dynamic conditions. So we coupled it with a color bounding box clipping similar to the one in temporal anti-aliasing. The only difference really is that we're dealing with scalar values, so it's a bit cheaper to calculate. And we use Marco-Salvi's formulation of the bounding box calculation using a 5x5 spatial filter to figure out the standard deviation. And while the result is not perfect and it still exhibits some noise, it is hardly perceptible once we actually combine it with the rest of the shading. To wrap things up, ray tracing makes it possible to replace refined hacks with unified approaches, making it possible to finally phase out artifact-prone algorithms such as screen space reflections, along with all the artist's time that is required to tune them. It is not a free lunch, though, as considerable effort needs to go into reconstruction and filtering. There is still a lot of research to be done. It is also just another tool in the box, and it should be used wisely where it makes the most sense. Before hardware catches up with demand, we need to be quite conservative in how we use our ray budgets. At the same, and we're only beginning to scratch the surface of what is possible with the technology. Even then, I think it's very encouraging that we can begin to approach the quality of path trace images with just over 2 rays per pixel. And finally, I would like to thank all those people who contributed to the PICA PICA project. It was an awesome and dedicated effort on the side of our team, but we also could not have done it without our external partners. And on one last note, I would like to point out that we're hiring for multiple positions at Seed. So if you're interested, please give me a shout. And this might leave us a few minutes for questions.
Thank you. Now,
Thank you.
time for questions. We invite here in front of the hall.
Now I have some water. Hello.
Hey, thank you so much for the talk. You mentioned for the reflection bilateral filter that you had a local estimate for the variance.
Mm-hmm.
Would it make sense at all to use that for picking new ray directions or similar, like to focus rays where there was much variance, either last frame or to refine the result?
Yeah, I was actually considering of doing exactly that. The variance estimate needs to be pretty stable, though. We do apply temporal filtering to it, so maybe it could work. Currently, we just have a constant bias of something like cutting the 30% of the primary sample space, but it might be a good idea to use the variance estimate as well. Yeah. Cheers. Anyone else?
That's a great chance.
Don't
waste it.
I'll only send our robots after you.
All right. Thank you very much. Don't forget to rate the lecture in our app. It's very important feedback for us and for people who present here. At 1 p.m. we have lunch. We have a premiere of a movie, We Are All Right. And if you want to join us for the next lecture here, please stay. Thank you.